The rational zero theorem, also known as the integral zero theorem, if and only if the leading coefficient Cn of the polynomial is equal to 1, which means the polynomial is monic in this case for integral zero theorem, but generally it's called the rational zero theorem. So if we have a polynomial p of x and it's equal to Cn x to the n plus dot 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 plus C1 x plus C naught, okay, and let x equal to a over b, which is a rational number, be root of your polynomial, and also that a and b are coprime or relatively prime, which means that their greatest common divisor or greatest common factor is going to be 1. Okay, so now I'm going to substitute a over b into x. Okay, so I substitute it into this equation, and I'm going to get this right over here. Because it's going to be a root, okay, or a 0, it's going to equal to 0 right over here. I also have two other conditions where the leading coefficient and the constant term, they are non-zero. All the coefficients are integers, and in here is a natural number, which are the positive integers. Now what I'm going to do is that I'll take this equation and multiply both sides by b to the n. So I'm going to get this equation. From here, two things are implied. Okay, so the first is this. I'm going to move this term to the other side. So I'll get this is equal to negative c naught b to the n. Then from this expression, I'm going to factor out an a. So I'll get this. Now notice here, it will be a times whatever this is, and that is equal to negative c naught b to the n, okay, which means that a divides into negative c naught b to the n. And this implies that a has to divide into c naught since GCD a comma b is equal to 1, which means that a does not divide into b, which means that a does not divide into b to the n. Okay, so in order for this to be true, okay, and a cannot go into b to the n, then a has to be dividing into c naught. The second implication is this. I will move this term right over here to the other side. Okay, so I will have dot 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 plus c naught b to the n is equal to negative c n a to the n. And then from here, I'll factor out a b. So I have b times dot 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 plus c naught b to the n minus 1. And again, b times whatever this is equal to this. So this means that b divides into negative c n a to the n, which means that b has to divide into cn. Since GCD a comma b is equal to 1, this means that b does not divide into a. This means that b does not divide into a to the n. So b has to divide into cn. That's pretty cool. Now, let's clean it up a little bit. So instead of writing the pluses and dot dot dots, okay, the ellipses, I can use the sigma sum notation. So I can actually rewrite this polynomial expression, okay? P of x is equal to the sum from k equals to 0 to n of ck x to the k, okay? And then plugging in a over b into x, I'll get this over here. And because it's a root or a 0, it equals to 0. And now I'll multiply both sides by b to the n. So when I multiply by b to the n, I can move the b to the n into here, and then it will be like this. So it will be b to the n divided by b to the k, right? And by exponent rules, it will be b to the n minus k, just like that. Okay, so that's what I have over here. So again, the two implications. The first one is that I'll take the term when k equals to 0, and I move it to the other side. So then here it starts from 1 going to n. Okay, and then I'll factor out an a over here. I'll pull it out. So when I pull that out, I'll get a times this over here. Okay, and by what I mentioned earlier with this, a has to divide into c naught. And the second implication is that I will take the term when k equals to n. So then the sigma will go from k equals to 0 to n minus 1. The term when k equals to n, I'll move it to the other side to get this. Now from this expression, I'll factor out a b. So I get b times this right over here. Okay, and again, based on what I mentioned earlier regarding this, we have that b divides into cn. and this completes the proof. Now I do want to mention something. So let's suppose we're going to have a monic polynomial. So the rational zero theorem more specifically will be called the integral zero theorem, okay, because the leading coefficient is equal to 1. So if the leading coefficient is equal to 1, so Cn is equal to 1 over here, and b divides into 1, then I guess the only thing what you can have is b is equal to plus or minus 1, okay? And that is because x is rational, which means a and b are integers. Now, I guess the integral zero theorem, or the rational zero theorem, but I'll just use the integral zero theorem for now, okay? So then we are only kind of just focusing on the constant term. The integral zero theorem, when you're looking at the constant term and its factors, okay, the positive and negative integer factors, it tells you what are the conditions in order for your x to be a root, okay? It necessarily needs to be a factor of your constant term. But just because you have a bunch of these factors of your constant term doesn't mean that all of them are going to be roots, okay? It just means that if you have a root, then that root must be a factor of your constant term. So the integral zero theorem is good at telling you what are not the roots, okay? So if you have, let's say, x to the n plus dot 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 plus, let's say 12 is equal to 0, okay? Then you know for sure that the number 13 cannot be a root to this polynomial. You know for sure that the number 5 cannot be a root to this polynomial. You know that the number minus 7 cannot be a root to this polynomial p of x, okay? Now, if it does have a root, then the roots must exist in this set. So we have the set of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and of course, plus or minus 12. So if it does have a root, then it has to be one of these guys. But depending on what the polynomial is, none of these could actually be the roots of this. Maybe this p of x doesn't have any roots. What I'm just trying to say is that if it does have a root, then it has to belong in here, okay? But it doesn't mean that all of these are guaranteed to be roots. You have to test each of them individually, which is what high school students need to do for questions like this, okay? I hope that helps.